When looking at lines, we can compare two or more lines in a few different ways. And the first is to look and see if those two lines are parallel. So what it means to be parallel, it means that if two lines are parallel, their slopes will be equal. Okay, they will never intersect. You may recall that parallel lines look something like this. And if you were to extend them in either direction, they would never cross. So in the case of linear relations, where we have equations of a line, if two lines are parallel, they will have the exact same slope, okay, because this indicates that the rise and run are the same in both lines, which means that it's impossible for them to ever cross at a point. So an equation of what that could look like, we could have like y equals, let's say, x plus 5. Okay, so that would be, if we were to graph that line on the grid here, my y-intercept, the plus 5 tells me it's at B, so that's the point that I would plot first. And my slope, there's no number written in front of the x, so that means that my slope is 1. So I'm going to just go up 1 over 1, right? 1 is the same as 1 over 1, rise over run are both 1, so I'm going to go up 1 over 1, up 1 over 1, and I would keep doing that to get a bunch of points. Okay, so then I would have my line like this. That's going to go through my points. So that could be maybe the equation of my first line. And then if I wanted to write an equation of a line that is parallel, I could have something maybe like this: y equals x minus 3. Okay, so just looking at the actual equations, you can see that here my slope is 1, right? We said when there's nothing written in front, it's an invisible 1 here. My slope is also 1 in the next equation. And I can check these lines out graphically and see what's happening as well. So in this case, y equals x minus 3. That means that my y-intercept is at negative 3, so that's the point that I can plot first. That would be right here. And then again, my slope is 1, so I'm going up 1 over 1. Over and over again. And then if I were to connect those points, oops, this is what I would have. Okay, and so we can see from the graph they look like they're pretty parallel, and if we were to extend them forever, they would never intersect, so there would be no point of intersection is what we would call that. So those are parallel. The key thing here, so obviously in these two equations that I wrote, you can see that this is obviously the same slope, but sometimes maybe it would be written as like a fraction that is not fully simplified. So like let's say you had a slope of 1 over 2, and then maybe your other slope was 6 over 12. From just looking at them initially, you might say those are not the same, so they're not parallel. However, that second slope, 6 over 2, we could simplify, sorry, 6 over 12, we can simplify to 1 over 2, so those would be an example of parallel lines as well, because the slopes actually are equal when you fully simplify the fractions. Okay, so that's just another example of how you could have parallel lines. The opposite to being parallel is being perpendicular. So perpendicular lines, it means that they intersect at a 90-degree angle. Okay, so if you think, I mean, we're just dealing with triangles, so like in a right triangle, two lines are going to cross at a 90-degree angle like this. Okay, and I could actually, sorry, make this continue on. So they would be something like this. So they will cross, they will have a point of intersection, and the angle between the lines when they cross is 90 degrees. When we were talking about linear relations specifically, their slopes are what we call the negative reciprocal of each other. So what that means is, let's say my first slope was negative 2 over 3. I'll use the same thing from the previous example that we calculated. So if my first slope is negative 2 over 3, then my perpendicular slope, I'm going to call it M2, but you sometimes will also see it like this, M perpendicular. I will use that symbol quite often, and that's to indicate the perpendicular slope. is equal to the negative reciprocal. So first of all, a reciprocal of a fraction means that we just flip it. Okay, so I've got 2 on the top, 3 on the bottom, so I just am going to swap that. I was just like, I don't know, I just pictured like the fraction doing a handstand, and the numbers are switching. So I'm going to have 3 on the top and 2 on the bottom. And when it says negative, this might make you think that it has to be negative. However, in this example I showed you, it's a bit different. So we are going to change the sign. Okay, so really what we would be doing, we would make this negative. It would be like negative 2 over 3, which is just a positive, right, if you have 2 negatives. So the way that I think of it the easiest is you flip the sign and you flip the fraction. Okay, so that's kind of the way that you are doing this. You flip the sign and flip the fraction. So if I wanted to take a look at what that might look like on my graph, I could have, maybe I would say, y equals negative 2 over 3 x minus 1. So if I were to graph that, I'm going to start with my y-intercept, which is negative 1, so right here. And then I'm using my slope to find at least one more point so that I can create the line. So my slope is negative 2 over 3, so I'm going to be going down 2 over 3. So I'll have 1, 2, 2, 3 here. And then I usually like to do at least one more point just so that I can draw my line a bit more accurately. So I would have a point here. Okay, and then I could connect those with a line. So I would have something like this. I'm going to show that it extends here. And then I'm going to also just extend it a bit further on this side. Okay, so that's my first line. And then if I had my equation of a second line, I'm going to use that negative reciprocal as my slope. So I'm going to have 3 over 2. And let's say I have y equals 3 over 2x plus 6, let's say. Okay, so my y-intercept is at 6, so that's the first point I'm going to plot. That's right here. And then I'm going, actually one sec, I'm going to make that a bit lower so that you can see what I'm doing on the graph a bit easier. So instead of 6, let's do 2. Just so that I've got space on the graph to go up 3 and over 2. So that point will be here. And then I'm going up 3 over 2. So my second point is here. I could do another point here. Okay, and then if I were to draw a line that connects those, then it would be something like this. Okay, and then again, it would extend infinitely in either direction. And so we can see, obviously, it might not be perfectly exact because we're graphing by hand, so there's a bit of room for error. But if we look at where these lines cross, this here looks pretty perpendicular, looks like a 90-degree angle. So that's what it would look like when you graph those lines. Okay, so these ones visually, you can see that it most likely looks like it crosses at a 90-degree angle. You would need a protractor to be certain. But graphically, if you're looking at the slopes, if you flip the fraction of your slope and flip the sign, then you would get the negative reciprocal, and that will tell you if the slopes of the lines are perpendicular. So just 2 examples to look here how we could write some equations that would, for lines that would be parallel to y equals negative 3x plus 7. First one I'm just going to look at, so my slope here is negative 3. So that means that all of my lines that I'm going to write here will have a slope of negative 3. Okay, so you can write an infinite number of lines that are parallel to this. So you could have y equals negative 3x, and then you're just making whatever y-intercept you want. So we could have like plus 1. You could do y equals negative 3x minus 100. Y equals negative 3x plus 26. Doesn't matter what your b value is, as long as your slope for the lines here is -3, then that means that your lines will be parallel. Now for this one, I'm not asking for it to be perpendicular, but I just want to show what the perpendicular slope for this would be. So actually first what I'm going to do, for -3, that doesn't look like a fraction, right? So it's just, there's only one number. However, your rise is 3, it's going down 3, and then if there's no number on the denominator, it's always just going to be an invisible 1 there. So if that helps you to see what it would look like to other fractions, so that we can actually flip it, our perpendicular slope, if we flip the fraction, it would be 1 on the top, 3 on the bottom, and then because it was negative, then we are just flipping the sign, so it would be positive. So the perpendicular slope would be positive 1/3. Okay, we don't need to use that for that example, but that's just showing how you would do that. So for the second example here, I want to write an equation of some lines that is perpendicular to y equals 2/5x minus 1. So first I'm going to write what my slope is, which is 2/5. And then because I want those lines to be perpendicular, I'm going to flip my fraction and flip the sign. Okay, so 2/5 was positive, so I'm going to flip the sign to be negative, and then I'm putting 5 on the top, 2 on the bottom. I like to keep them as a fraction. Okay, I know a lot of people are scared of fractions. They don't like them, which is understandable. However, it's easier to tell that they're perpendicular if you leave them as a fraction. If I were to simplify that and write -2.5, then it's not as clear that it is perpendicular, because from the decimals you can't tell so easily. Okay, so if I wanted to write some lines that are perpendicular to the given line, I just need to make sure that their slope is -5/2. And then it doesn't matter what the y-intercept is, so we could have like -3, we could have +10. Again, there's infinite options for how, or for the number of lines that you can create that are perpendicular to that. You just need to make sure that your slope is the correct slope, -5/2, and then you can make the y-intercept whatever you would like, and it will be perpendicular to the given line.